All right, we're going to wrap up unit number 3 with the fundamental theorem of algebra. So what we're going to do with this is we're going to take everything that we've studied in unit 3 and we're going to take it all and put it all into one section here. So some of these questions are going to take a long time and they're going to be sort of complicated to answer. So in problem number 1, we're asked, what are all the roots of x to the 5th minus x to the 4th minus 3x cubed plus 3x squared minus 4x plus 4 equals 0. The number of roots that we have is 5. That's the fundamental theorem of algebra. The number of roots or the number of solutions is always going to match the lead exponent. So in this case, the lead exponent is x to the 5th. So we know that we've got 5 x's. We know that we've got 5 solutions. The next thing we're going to look at is what are the possible positive roots? And to do this, we're going to use Descartes' rule of signs. So we've got positive, negative, negative, positive, negative, positive. So what that tells us is that there are 4 sign changes. So if you've got 4 sign changes, you can have 4 positive roots, you can have 2 positive roots, or you can have 0 positive roots. Now remember that the way that we figure out if we've got 4, 2, or 0 is anytime that we have imaginary roots, they always come in pairs. So if you've got 2 positive roots, that means that you would have to have 2 imaginary roots to get to your 4 that Descartes gave you. Then the negative roots, we're going to put in -1 for each of the x's, and that gives us negative, negative, positive, 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 positive. And since we've got 1 sign change, that means that we've got 1 possible negative root. This means that our possible imaginary roots are 0, 2, or 4. So the way that we get this is we say, if we start off with 5 roots and 4 of them are positive and 1 of them is negative, how many are left for imaginary? Well, that would be 0. Then if we have 5 roots and we have 2 positive roots and 1 negative root, how many do we have left over for imaginary? We've got 2. If we have 5 roots and 0 of them are positive and 1 of them is negative, then how many are left for imaginary? That's 4. So when we do this, again, all of our imaginary roots are going to come in pairs. Since we're doing Algebra 2, we're only ever going to have a maximum of 2 imaginary roots because we don't know how to solve for 4 or 6 or 8. So you'll never go beyond just the 2. Then we're going to find the factors of p. And in this case, p is 4, so we've got plus or minus 1, plus or minus 2, plus or minus 4. We're going to find the factors of q. q is positive 1, so we've got plus or minus 1. Then we're going to set up p over q. Now that we've done all this is all the legwork. This is to get us to the point where we're now going to start checking on possible solutions. The next step is to actually go in and start looking at what are our x's. So we're going to use synthetic division to do that. Since this is Algebra 2, and I know that I've got at least 2 positive roots, and I've only got 1 negative root, what I want to do is I want to test out the positives first, because I'm more likely to hit a positive root first before I hit the 1 negative root. Now, what we're going to do with this is we're going to, again, put this into synthetic division. So I'm going to set it up with my half box as 1, and then I'm going to go 1, negative 3, 3, negative 4, and 4, all of the coefficients of the original equation. Then bring down the 1, multiply by 1, so you get 1, add, subtract, you get 0, multiply, 0, add or subtract, you get negative 3, multiply, you get negative 3, add or subtract, you get 0, multiply, you get 0, add or subtract, you get negative 4, and then multiply again, you get negative 4. And what we'll see is 4 minus 4 is 0, so we're left with no remainder. This tells us that 1 is a solution. So what we're going to do next is it's possible that 1 is a solution twice. So we're going to run through 1 again, but this time we're going to do it against the line that we created in the last synthetic division problem, the one that's underneath the bar. We're just going to drop the 0. So we're going to set up our synthetic division with 1 as in the half box, then 1, 0, negative 3, 0, and negative 4 in the line with that box. So when we do this, bring down the 1, multiply by 1, we get 1, multiply by 1, we get -2, multiply by 1, we get -2 again, multiply by 1, this time we get -6. So since our remainder is -6, we know that 1 is only a solution one time. So we're going to move on and try out number 2. With this, again, half box with the 2, use the numbers that were under the bar from the first one, which is 1, 0, -3, 0, -4, and then run through your synthetic division again. When we do this, our bottom row is going to be 1, 2, 1, 2, and 0. Since we get that 0 again as the remainder, that tells us that 2 is a solution. So as of this moment, I know that 2 of my solutions out of the 5 are 1 and 2. Here's where it gets interesting. Usually when you're doing synthetic division to find these solutions, you want to keep doing synthetic division until you get down to a quadratic. So right now with 1, 2, 1, 2, we have a cubic polynomial. We've got x cubed plus 2x squared plus x plus 2. So again, normally what we would do is we would do synthetic division again and see if we can knock that down to a quadratic function. But if you notice the arrangement of the numbers here, 1, 2, 1, and 2, we could actually go and do grouping at this point. It's basically that grouping and sum or difference of cubes are the only ways that we know how to factor cubic polynomials. We could do grouping at this point. I'm going to go ahead and carry on though with the synthetic division just to show you what that looks like. So again, we need to get down to a quadratic. And what I'm going to do is I'm going to switch over to the negatives because I may not have any more positive solutions. So I'm going to try -1. So put -1 in the half box, and you got 1, 2, 1, 2. When we run synthetic division through, our bottom line comes out to 1, 1, 0, 2. So since that's a remainder of 2, that's not our solution. So try out -2. When we do -2, we get 1, 0, 1, and 0. So when we do this, we can see that we've got a remainder of 0, which means that we're down to a quadratic solution. So we can change this from 1, 0, 1 over to x squared plus 0x plus 1, or simply x squared plus 1. Now, since we don't have a bx term, we can just isolate the x. When we isolate the x, we move the 1 over to the other side. We get x squared equals -1. Take the square root of both sides, so the square root of x squared equals the square root of -1, and that means that x is equal to plus or minus I. That means that all that we had left was 2 imaginary solutions. So when we go back to our whole big list of things that we need to find, our roots are going to be 1, 2, -2, and plus or minus I. And you can see that we've got 5 solutions there, which matches the lead exponent of the polynomial. In problem number 2, we're told to use a graphing calculator and find the roots of x to the 4th plus x cubed minus 7x squared minus 9x minus 18 equals 0. So when we plug that into our graphing calculator, we end up with x-intercepts at plus or minus 3. So this means that we only have 2 real solutions to our problem, positive 3 and negative 3. If we look at that lead exponent, we see that the lead exponent is 4, which tells us that there are 2 more roots to this problem, or 2 more x's to this problem, which means that they're both going to be imaginary numbers. So since we know that 3 and -3 are both solutions to this problem, here's what we're going to do. We're going to go in and we're going to use synthetic division to find out what is the quadratic equation that we're left with when we divide out 3 and the -3. So when we use synthetic division, divide out 3, we're left with 1, 4, 5, 6, and 0. We should have gotten that 0 because we know that 3 is a solution. So then run through -3 on 1, 4, 5, and 6. When we do this, you can see that again, the last spot is a 0, and we're left with 1, 1, and 2. this means that we've got x squared plus x plus 2. With x squared plus x plus 2, we're going to need to go in and use the quadratic formula because there's not going to be any way to factor this. So when you set up quadratic formula, go ahead and do that. Plug everything in where it's supposed to be. Start working it down. And you see that we end up with -1 plus or minus the square root of -7 over 2. You've got to take that I out from underneath the radical, and you're left with x equals -1 plus or minus I square root of 7 over 2. This means that your solutions are that, the -1 plus or minus I squared of 7 over 2, and plus or minus 3. So we've got all 4 of our solutions for this problem.